Okay, guys, let's move on. So we're going to do some big O notation. Big O notation gives you a measure of the time complexity of an algorithm relative to the size of the problem. Basically, we're given an input size, and we need to find out how many steps that input is going to take. Okay, how many steps this input is going to take. Is going to need to complete. All right. Now, this is quite nice if you just kind of know how this, if you can kind of just apply this. Okay, looking at this question, you only need to know this, and you can kind of treat these as a function. If you're not even sure, you can just plug something in. Okay, so let's say my n equals 8. Okay, let's say my n equals 8. Well, we've got the complexity, which is going to output basically n squared number of inputs. Well, yeah, n squared of the inputs, so input squared. So this is going to be 8 squared, so that's going to give us about 64 steps. Okay, if I then do log 2 of n, so let me quickly explain how log 2 of n works. Let's do this up here. So if I were to go 2 cubed equals 8, what log does is basically allows us to rearrange this. So I can do log 2 of 8 equals 3. So the idea is you take this 2, plug it there, take this 8, plug it here, and then we can work out what this power is. So we can say 2 risen to the power of what, okay, equals 3. Sorry, 2 risen to the power of what gives me 8. Root 2 given to the power of what equals 8. And we can figure out there's actually 2 to the power of 3. Okay, so in reality, in computer science, that kind of helps us with, we start with this, how many times do I need to half a number before we can't half it anymore? That's normally what you use the log for in computer science. Okay, but what the log is allowing us to find, well, 2 to the power of what gives me 8, and we can find out that's 3. And in computer science, that helps us find out how many times we can halve something before we can't halve it anymore. Okay, if I were to plug this in, well, log 2 of 8, right? So that'll be log 2 of 8. That's going to give us 3. Okay, and then finally, big O of n factorial. So that's the equivalent of 8 times by 7 times by 6 times by 5, dot, 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 dot. Without even calculating it, you can see that it's bigger than 64. And you can see that this is going to give us loads and loads of steps. So it's not very efficient, right? Given the same input, this is giving me 3 steps. It's going to take 3 steps to do something. This is going to take 64 steps to do something. This is going to take a lot more than 64 to do something. So we can really quickly say most efficient is this B. And then least efficient, well, we can find out that it's definitely n factorial, which is C. Okay, so let me now move on to the next stage. I'm just going to rub out some things. Okay. One moment. Okay. Nearly done. All right. Using the big O notation, express the complexity of the following pseudocode. Okay, so we need to figure out how many steps this is going to take. Okay, well, that's technically one step. Okay, and now we can just figure what's going on here. So actually, let's plug in an 8. Let's plug in 8 again. I equals 8. Right? What does this mean? Well, this is saying we need to divide this 8 by 2. Okay, so we've got a 4. And we're going to keep going until while I is greater than 1. So when I get to 0, when I go, so div basically gives me, it's going to get rid of the decimal. That's what div does. So instead of 0.5, it's going to give me 0. Division is division, but you get rid of the decimal. So here, we're going to output this. That's what's happened. This is a measure of how many times I can divide 8 by 2. That was literally exactly my definition of log 2 of n. Right? So, because I said that 2 to the power of 3 equals 8. So if I do it this way around, we can go 2 to the power of 2 times by 2 times by 2. So 2 times by 2 times by 2 gives me 8. But in computer science, normally you can go the other way around and divide by 2, divide by 2, and divide by 2. In computer science, it's normally a measure of how many times you can divide something by 2. So here, this is perfect log 2 of n. This is perfect log 2 of n. Yes, we've got this plus 1 involved, but in computer science, for big O notation, we only take, so this is like the official, like if you're being really technical about it, because there's a plus 1. And in big O notation, we only take the most significant component so that you can describe the complexity like this. Okay, let's move on. So now we can see how many steps is this going to take. This is going to take n steps. Okay, so we've got n. And everything inside this is going to be done n times, right? That's exactly what it's asking. So we've got n times by whatever's inside these brackets, where it's going to be, oh gosh, another n. Because you can see I1 to n, that's n steps. Everything inside this, because it's a for loop, is going to be done n times. So we've got another n. Okay, so that's done. And everything inside this is going to be done n times. Well, what's going on here? Well, that's another n things, right? So n times by, so n times by n times by, and you're going to get, and then n lots of, oh, this is just one step, right? So n lots of one step. So this is literally going to give you n cubed. This is the biggest component, the most significant component in the complexity. So it's going to be O(n) cubed. Right, so we can see we've got an n, then everything inside that loop is going to be multiplied by n times. So the first n's there, that's going to multiply all of this, and then, but this has become, we've got an n multiply by the other internal of this loop. So we times by n again, and then it will be times by 1. That's what's happened. Next question is calculate the number of times an output statement is executed in the subroutine big O A list. They said show below, but I think they mean shown above. Yeah, fantastic. So let's kind of figure out, in general, how many output statements there are going to be. Well, this bit is going to be run. This for loop means that everything inside it is going to be run n times, right? Everything inside this is going to be run n times because that's exactly how a for loop works. You're going to have n multiplied by. Now, is there an output statement in this section? Oh, look, here's one. Therefore, we've got one output statement. Okay, any other output statements here? Not yet, not yet. Oh, but we've got another for loop. Okay, and the for loop is 1 to k. Right, well, what's k? Well, do we want k? No, we want n, right? We want in terms of n. So we're going from 0 up to n over 2 minus 1. Because we're not starting from 1, then it's this minus 1 kind of, because if I was going 1 to n over 2, would be happy, right? But if I go 0 to n over 2 minus 1, we're also happy. So it means we've got n over 2 steps. Hopefully that is clear. So basically, just like above, when I said we've got n steps here, because we're going 0 to n minus 1, we're going 0 to n over 2. So it's just like this. Okay? And now we've ended this loop. And the reason I'm saying n over 2 is because there are n over 2 outputs that occur here. Oh, look, there's an output statement. So therefore, we need to care that this has an output in it. Okay? And then after everything, we've also got another guy here. So we've got another one output here. So to reiterate, we've got a for loop, we just run n times. Everything in this for loop, therefore, is run n times. So we go through and we multiply everything. Well, what's in this for loop? We've got a 1 because we've got an output here. And then as we're going along, we've realized we've got another for loop. Right, so it's going to go like this. This is our loop again. Okay, and we realize that then, well, we've got n over 2 loops happening. And that means we've got n over 2 outputs happening. Yeah? And then finally, right at the end of everything, we've just got another output at the end. We want a parameter list of 6 items, so we just plug 6 into here. 6 multiplied by 1 plus 6 over 2 plus 1, which becomes 3 times by 4, not 3, sorry, 6 times by 4 plus 1. Now we've got to express the time complexity using a big O notation. So let's bring this back in again. We've got n1 plus n over 2 plus 1. That was our equation, right, for the number of outputs. Well, let's just expand this out, right? So n times by 1, n times by n over 2, well, that'll be n squared over 2. Then we're going to have plus 1 on the end. What would you say is the most significant component of this? Right, well, so our components can either be a 1, a log n, an n squared, or n factorial, or you could also get in potentially 2 to the n. Right? What's the most significant component? Well, this we've spotted an n squared. An n squared exists. If an n squared exists and there's nothing more complex than an n squared in there, then it's big O of n squared. And that's that.